So here we would be ready to go on and compute and discuss the algorithm to update this classifier up till it make a good classification. This will be indeed the argument, the perceptron algorithm. However, we take a little bit a route more general, and we are going to discuss some problem that we have more general before we are going really in detailing the perceptron algorithm. We need indeed to develop a method to generally deal with learning algorithms in the context here of supervised learning. And we are given a set of features and associated labels, and we want to learn these parameters. So the algorithm will have some parameters that are those elements that will be learned by the algorithm itself by processing the data, the couple between x and y. And these parameters are learned endogenously by the algorithm. However, there will be in general other parameters that we call hyperparameters that will remain constant during the learning step of the algorithm. So the idea is that these additional parameters still affect the performance of the algorithm, but are not learned by the algorithm itself. For example, to take some algorithm that we will see later, the number of neurons in a neural network layer. This is defined before the parameters of these layers will be learned by the algorithm, or the number of individual decision trees in random forests. Or in many cases, and including here we'll see the perceptron, how long should the learning step continue. And here we can take different forms depending on the specific algorithm, but in general one hyperparameter will decide how deep continue the learning step. And hyperparameters are very important because they play a fundamental role in the trade-off between specialization and generalization. Indeed, the objective of training is not to learn the relation between the x and the y that we provide to the algorithm. It's not this. It is rated to learn the general relationship that exists in the nature of the data between x and y for all the population from which x and y are sampled, and not from the one that we provide specifically to the algorithm, okay? So the hyperparameters should be set to the levels that maximize this second objective, not the minimization of the errors of the data that we provide to the algorithm, to train the algorithm. So for neural networks, if you use too many neurons, or in general, if you train too much, we would learn the specific relation between x and y in the training data. However, this reflects the specific data that we provided and not the general population. And this concept is exactly the same, the one that we have in statistics, where we speak about overfitting of the model. That is, it generate too much variance in the parameter of the model, but this because the parameters will depend on the specific x and y that we provide to the algorithm. If we overfit our model choosing the wrong hyperparameters, we'll end up that providing the algorithm with different training data, we will have very different training parameter of the algorithm. At the opposite, if our model is too simple or simply receive too little training, we have the opposite problem, and we have too much bias, and we'll not be able to learn the relationship between the x and the y in a sufficient way. So how can we turn an algorithm that fit very well the training data, but then generalize very little? Well, one way is to reduce the training step, but other than that, we can find some technique that allow the algorithm to generalize in a better way at the expense of performing better on the training data. And this technique that we use in the algorithm are called regularizations and will take the form of some hyperparameters that work on this trade-off between bias and variance. So then how can we choose these hyperparameters that play the role in this bias-variance trade-off? As we put no assumptions on the data except that they all come from the same populations. So how can we choose these hyperparameters in general? And one general way to choose the hyperparameters, whatever is the algorithm, is to use different datasets to evaluate the algorithm efficiency in finding the relation between x and y, but also the efficiency in generalize outside of this training data. So one idea is to split our dataset in 3 different subsets. Okay, the training set will be the one that is actually used to find the parameter of the algorithm, to train the algorithm to learn the relation between the x and the y. And this will be conditional to the hyperparameters that, so here again, are not touched during the training set. So this training set works conditional to the hyperparameters. A second set, normally this training set is the bigger one. A second smaller set is called the validation set, but we use to evaluate the results of the trained algorithm on data that importantly has not been used to train the algorithm. So the idea is that we have some hyperparameters. With this hyperparameter, we feed with training set with the training data. We obtain some the training step will find the parameters, and with this parameter we work on the validation set and we find how good is the algorithm with data that has not been used for training. Finally, so we do this one normally various times for various hyperparameters until we find the best hyperparameters that the generalization is the best one. After we found the optimal hyperparameter, again we train another time the algorithm with all the training, or sometimes the training plus the validation. So we train again our algorithm with with those that we believe are our better hyperparameters, and we find finally the parameter of the algorithm, and we use finally the test data to evaluate the overall performance of our algorithm. Why we do this? Because again, these hyperparameters are conditional to the data that we use in the validation set. So if we use this validation set to judge the validity, how good is our algorithm, we risk to overestimate how good our algorithm is. We really need to find something to use the algorithm on some data that has never been used, neither for finding the parameter nor for finding the hyperparameters, and this will tell us really how much confidence we can put in this algorithm. And in practice, we have various ways to find these hyperparameters thanks to the validation set. We can make a grid search over the space of the hyperparameter. So we, for example, if we know that neural networks layers are in a certain range, we can just go and check every integer in the range or every 5 in the range if this range is very big. So we can make a grid search over the space. We can make randomly, or we can use also for the hyperparameters some gradient-based methods. In all cases, it will be independent on the specific algorithm founded to find the parameter. While it is true that to validate the model, we need to use data that has not been used to train the model. This differentiation doesn't need to be the same at each step. And in particular, dividing the whole dataset in 3 parts may be expensive, in the sense that if we have few data, we end up dividing by 3, which will have very little data to validate or test or training the algorithm. So if we have a problem of few observations, we may be better off employing a technique called k-folds cross validations. But is nothing else than repeating this step, but changing the data that are part of training and validation at each step. That is it. We first divide our dataset in 2 parts. One remains our test part, and we put it aside. The other one is the data set that for which we'll train and validate the algorithm. At this point, for each possible combination of hyperparameters, for example, first layer for 4 nodes and second layer 5 nodes, or using 30 decision tree and so on. So for each fixed combination of hyperparameters, we divide our training and validation set in n types, in k types. Here we use 5. Another common is to divide by 10, so use 10 folds cross validation. So we divide our training and validation set in 5. We train the model a first time over the first 4, and we validate the model on the last of the 5 sets, and we repeat the process with keeping the validation set always the remaining subset. So here we'll have the validation set that will return some accuracy of the model or some error of the model. Here we'll have another error. Here we'll have another error, and so on. And then what we have is that we can have the average and the standard deviation of the error for that specific hyperparameter combination. So at the end, we can find an average error for these hyperparameter combinations. We can repeat for another hyperparameter combination. We can repeat for another hyperparameter combination, and so on, until we find the combination of hyperparameters that produce the lowest average error. We can also look on the standard deviation, so we can make a trade-off if the standard deviation of one combination is very low, even if it's not the lowest error absolutely. And at the end, we choose the combination of hyperparameters that minimize the error, and with that combinations, we again train the model of all these training and validation sets, and we judge the final validity of the model on the test set. So this is something very general that we'll use in all supervised machine learning technique. Doesn't matter if simple or complex. It's the way that we'll find the parameter based on the training and the hyperparameter based on some sort of simple or cross validation. Now we are finally in the position to look for the algorithm that will help us to turn this hyperplane to improve the classification. That is the perceptron algorithm.